All right, my name is Reed, and along with my partner Sam, we are going to be talking about our ECE project, the second one and final one you complete with Gokirmak. Now, some things to note before we start talking about our circuit. Our design will not be talking about any kind of volume control, which includes tuning the aux input, the microphone input, and the volume of the speaker. So please know that during this video, we won't be discussing that because it's not implemented in our circuit. Also note that we did not amplify our microphone's AC signal before we mixed it. You will want to do this, but we simply didn't have time to do it for our design, and that's another thing that won't be shown. And lastly, we don't have a design for shooting the laser at very long distances. This circuit will work at long distances. However, with the small photodiodes that we had to use for this design, it's extremely hard to aim the laser at long distances. And we also didn't have time to design a method for aiming more accurately. So that also won't be discussed, but do note that it does work from long distances. It's just the aiming that is hard to do. Briefly, here's the setup for the microphone. You can see that we have a voltage supply going through a resistor, and that's in series with the microphone, and then it's grounded. So the microphone is essentially just a variable resistor. When noise is introduced to it, it will change its resistance. So what you want to do is measure the microphone's natural resistance at whatever room volume you're going to be testing at, and then pick some R value really close to it, if not the same value, to be in series with it. That's your first resistor. So what this will do is create a voltage divider with an equal voltage in the middle, and you can then take that voltage, that's what's leading out of the middle, and that will have an AC signal in it when you introduce noise, because when the resistance varies, the voltage in the middle will also vary, and it's going to be a very small variance, but we'll talk about that later. Something also to note is that the voltage signal that you're pulling out of that middle node will need to be amplified because it's very small, whereas the aux signal, that input can usually just go straight into your summing op amp. All right, so this is the transmitting portion of the circuit. You'll see in the very far left that we replaced the microphone and aux input with just a sine voltage wave. The reason this was done for the design right now is just to simplify what you're looking at. So we have a capacitor is the first thing that the wave will go through. And what this essentially does is buffers the DC signal. It will completely remove it so that only the AC comes through, which is important for isolating and amplifying the AC signal. So we have an op amp with -9 and 9 volts supplied to it, and there's a negative feedback loop with 180k ohm resistor and a 33k ohm resistor going into the negative input, and the positive input is grounded. So what this will do is create a larger AC signal wave at the output, because the input you'll find from your aux and microphone, the DC variance is very, very small. So by passing it through this loop, we essentially get a much larger amplitude in our wave, and that will make the signal a lot clearer when you transmit it with your laser. So at the output of the op amp, we have it leading into a bias T. So this setup essentially allows you to combine AC and DC signal without the two combining and messing up their own separate parts of the circuit. So the output goes through the capacitor, so the AC signal is completely unaffected. You'll still have the same amplitude in your wave. And the DC signal will come through the inductor. And since the inductor will short after a certain amount of time, you'll get whatever you're supplying straight across the laser. But the setup is important because the voltage from whatever you're supplying through the inductor won't be able to go back and affect the op amp part of your circuit because of the buffer the capacitor creates, and the AC signal won't be able to go through the inductor and therefore split before it gets to your laser. So by having this setup, you'll be able to add a DC voltage to light up the laser to your AC signal without either of the two affecting one another or the rest of your circuit. You might need to change some of your capacitor or inductor values depending on how the rest of your circuit is built. Your values probably will not be the same. We actually had to eventually change one of the inductor values during our design to get a better noise. So definitely play around with the values if your initial design doesn't work out.
Are designed for the receiving end of the circuit. For the receiver, we have a photodiode connected to the ground and then to a capacitor of 0.01 microfarads. The photodiode receives both AC and DC signal from the laser and it sends it to the capacitor. The capacitor acts as a blockage for the DC signal and only allow AC to flow through it. So from this point on, the only signal that is being transferred further into circuit is AC signal. This signal is then sent to an op amp, and here we're using inverting op amp. This is because of the resistor value that we are using, our op amp is actually getting saturated, and then the output from this op amp is fed to the speaker, and we noticed that our speaker was not playing at a good amount of volume. So to increase the volume, we had to increase the current running across it. So to do that, we made a same inverting op amp and added in a parallel with the previous one, and the output from both of them is being sent to the speaker. Since we know that the power depends upon the square of the current, so just by increasing the current by double, we actually get a 4 times gain. So this is our receiving end of the circuit.
Now, briefly before we show the testing, just keep in mind that we are testing at extremely close range, like only an inch away. And the reason for this is because, like I mentioned before I started the video, that it's extremely hard to aim the laser from long distances. We didn't record any footage from our actual testing session, but you can trust me that the laser does work on the photodiode at long distances. It just has to be a head-on shot, and you have to aim it very accurately. You'll also see that we both have both the receiving and transmitting circuits on our board. However, they're the exact same design, so we only showed one test case of my circuit transmitting to Sam's board.